All right, welcome back. Any questions, please? What questions do you have about the material homeworks that we discussed so far? Okay, let's see. Nothing in the chat. So I will give you some hints about the upcoming midterm. Okay, uh, like I said, and then let's see. We finished chapter 12 in the last class, and I mentioned I'm going to give you some hints on how to study for chapter 13. Okay, the idea was that you should have looked at the videos by Professor Pedro and also started working on the homework problems. Okay, the midterm, like I promised, is it does not have body part questions. Okay, and it will be available from 4 p.m. on the 24th, on the day of the exam. Okay, there are 6 questions. Now, the first question and the second question as well are about partial fraction expansion. Okay, mostly the first problem is mostly about a transfer function, about a function which has real and distinct roots for the denominator, or it may have complex and distinct roots. Okay, it may have complex and distinct roots as well. Okay, the second problem is mostly about complex and distinct roots. If the um, S domain expression has denominator, the fraction is proper, and it has a denominator for which the roots are complex and conjugate pairs distinct. How do you write the partial fraction expansion of it? Okay, and maybe how do you go from the partial fraction expansion to time domain? Okay, then there is the initial and final value theorems. How do you use the initial and final value theorems, okay, to calculate the initial value of your function and the final value of your function in the time domain? Okay, these are the definitions for initial and final value theorems. Right? So that's question number 3. Now, question number 4 is on material from chapter 13, right? 1 to 3 is all chapter 12. Okay, question number 4 is on chapter 13, which is S domain equivalent of a capacitor and inductor. S domain equivalent of capacitor and inductor. Okay, very similar. If you remember, we will talk about it today. Briefly, we'll talk. I'll mention it today. Then show you the similarities between the S domain and the frequency domain. And I will also point out where the S domain takes into account the initial conditions as well. Okay, then the idea of transfer function, V out of S over V in of S. Okay, that's the definition of transfer function, the output over input. Okay, and then if you're able to manipulate your KCL and KVL equations into this form, Vs over Is, the resulting S domain expression is called a transfer function. Okay, given a circuit with R, L, C components, you should be able to set up KCL and KVL expressions and massage that in this form. Okay. Now, the other problem number 6, of course, is trying to find the V or I in the S domain. Pretty similar to what we did earlier. Okay. In the last class, I think I showed you a problem where the current is given, or something like this. Okay, R, L, C, and you're asked to find out some other current, I0. What is the expression for I0 in the S domain and in the time domain? Okay, some spin, okay, some twist on that um, mode of questions. Okay, but these are mostly, well, not mostly. This is just about all the questions that you can expect on the second midterm. Okay, and this is going to become available to you on Google Drive, so you don't have to frantically copy. Okay, questions, please. What questions do you have? Okay, if you don't have questions, then we can go ahead and get started on chapter 13. Okay, your first line of preparation material would be Tetros videos, and your next line of preparation would be your homeworks. And I'm just here trying to give you some hints, some insights, some big picture details. Okay, that way you can understand the big picture and keep the perspective intact. Okay. Let's see. So the idea of Laplace transform, this is what we have done in chapter 12, right? We understood the definition, the integral definition. If there is a function, you put an integral around it, multiply it by e to the negative st dt, okay? And take an integral of that function. That's the definition of Laplace transform. And what we saw is that this kind of transformation, okay, represented as f of s, has many advantages. One of the advantages is that it converts differential and integral terms of popular or frequently used circuit signals. It converts them from integral and differential forms into polynomials. Polynomials are easy to manipulate. Okay, and these also inherently include the initial condition. Okay, so essentially, when you're doing a Laplace transform, you're converting from the time domain to a frequency. Okay, you're converting from a time domain to a frequency. Okay, now time domain volts, in frequency domain you have volt seconds, amperes converts to ampere second, ohms converts to ohms. Okay, that's something you want to have in the back of your mind, just so you can make sure, do some quick sanity checks using the units in time domain and frequency domain. Okay, so the big meat of the chapter 13 is this idea of circuit elements in the S domain. Okay, there is the resistance, there is the capacitance, there is the inductance. These are the three circuit elements that we have seen in time domain and frequency domain, if you remember. Okay, the frequency domain of a resistance was R. Okay, and in this chapter we are going to look at the S domain equivalent. Okay, similarly, the frequency domain equivalent of capacitance was anybody remembers the frequency domain equivalent of a capacitance? One over j omega c, right? This is the frequency domain equivalent. So we are also going to investigate its S domain of a capacitance. Okay. Similarly, the same thing for here as well. Okay. For an inductor, the frequency domain equivalent was j omega L. Right. Now we are going to understand what it appears to be in the S domain. Okay. In the time domain, we had C and we had L, right? And then the equations we were setting up using C dV by dt, I equals to C dV by dt, or L di by dt. Okay, so instead of using those, we were earlier using J omega L. Okay, J omega L or ZL. Okay, this was ZL, remember? And this was ZC. Okay, and this is resistance and frequency domain. Okay, so the idea is we are going to look at these three circuit elements in the S domain as well. Okay, I'll spare you the calculations. Dr. Tetro does all of that. Okay, in his videos. I jump right to the conclusions. Okay, I'll simply show you the final result. Okay, and that way you can keep the big picture in mind, and then you can fill in the details about the calculations later on. In the time domain, the resistance is R, and in the S domain as well, the resistance is still going to behave like R. So the relationship, little lowercase, is a time domain. The capital letters, that's in the S domain. Okay, so the resistance does not change. Resistance has no frequency dependent terms in it. So the resistance is still going to have an ohmic behavior. Okay, whereas the inductor, okay, let's pay attention to the inductor. The inductor is just an inductor L in the time domain. In the frequency domain, earlier, if you remember, we just had J omega L, one inductor. The equivalent in frequency domain was J omega L. It's pretty similar here. Instead of J omega L, I have SL. Okay, so that part is still the same. Okay, that part is still the same. The only thing that has changed is this guy. Okay, there is an initial condition. Okay, so the inductor in time domain could be expressed in one of the two forms in S domain. Okay, so pay careful attention. Let's pay careful attention. I could express the inductor from a time domain as an inductor SL in series with a voltage Li0. That's one representation of it. Or if you need a current representation, you can represent it as an inductor SL with some current I0 S. I0 over S. Okay, let me write this is I0 over little s. Okay, so one of two ways the inductor could be represented. Okay, so S times Li minus this initial condition, or the V over SL plus, so V over SL plus IO over S. Okay, so it could be expressed in one of those forms. Okay, the only thing that you want to remember though is, if in the problem, okay, in the problem, if it says initial conditions are zero, initially, you see this on the homework, you see this on the exam, and uh, oftentimes, not always, but sometimes you see that the initial energy stored is zero. What it means is simply this guy is zero. Okay, so let me clarify. If the initial conditions are zero, okay, then what happens is this part of the circuit disappears. Okay, that part of the circuit disappears, and what you will be left with is simply very straightforward representation. Okay, very straightforward representation, um, as if you were in a regular frequency domain. Remember, this is j omega L in the frequency domain. If the initial conditions are zero, the S domain equivalent is SL. Similarly, if the initial condition is zero, okay, this is going to be SL. Whereas earlier, in frequency domain, we had j omega L. Okay, chapter 9, remember? Frequency domain. Now we are talking about S domain. S domain, you can simply, j omega L is the equivalent of S in this case. Okay, so there is a correspondence and there is a similarity between the frequency domain and the S domain. When the initial condition is zero, they are essentially the same element. I think so. Natalia has a question. Would you still be able to check the questions, answers? I think so, but I can double check that before we leave today. In case I forget, please remind. Okay, so the inductor can be expressed as a series combination of a SL and a voltage source. Okay, or a parallel combination of two currents. Similarly, the capacitance, the exact same thing applies. Okay, the important thing is, if the initial condition is zero, if there is initially no charge stored on the capacitance, it becomes 1 over SC in the S domain, 1 over j omega C in the frequency domain, and C in the time domain. Okay, this is the time domain, this is the S domain, and this is the frequency domain. Okay, but in other words, the capacitance nonetheless can be expressed as the capacitance with a voltage source V naught over S in series, okay, or a current source C times V naught, okay, the current source whose value is C times V naught in parallel with this capacitance, okay. And that's the reason why you see this negative C times V naught owing to the polarity in the opposite direction, okay. Okay. Here, pay attention to the polarity, negative and positive in this um, circuit element, which leads to negative Li0. Okay. The direction of the current is along the voltage drop. Therefore, um, that voltage drop is considered to be positive. Okay. All right. So that's about the circuit elements: the resistance, inductance, and capacitance in the frequency domain. Okay. So when it comes to applying these, that's straightforward. Okay. So when you're looking at a problem that's similar to this, all you have done is you replace this guy, okay, a capacitance with 1 over SC, okay, and you can ignore that voltage term. You can ignore the voltage term because uh, of this information. The switch has been closed for a long, long time. Okay, when the switch has been closed for a long, long time, what it means is that the capacitance and the inductance are fully discharged. There is absolutely no energy stored in them. What it simply means is that initial condition is 0. Okay, therefore we can ignore this guy, and we are left with just the 1 over SC term. So this resistance is this guy. This inductor is replaced using SL. Okay, that is because of the initial condition. Okay, because the initial condition is given to be 0. Okay, and then it's simply a matter of you call this ZC, you call this R, and you call this ZL. Okay, you have a parallel combination of ZC. Let me write it ZC in parallel with R, in parallel with ZL. Okay, so it's easy to find the Z equivalent. Okay, once you have the Z equivalent, you should be able to find the V. Okay, or you may not even need to calculate Z equivalent if that is not necessary in certain times. So all you have done here is in analyzing this problem, you're asked to find this V. Okay, so the problem that you're going to see on the midterm exam is going to be something similar to this. I'll give you a circuit that has RLC components. Okay, of course, I'll give you some numbers. Okay, but you don't have to plug these numbers in right at the beginning. Okay, what would be best is to solve your problem symbolically. Okay, using all these S, R, and C. And once you arrive at this final result, then you can plug in for the value of R, how much ever that is, 625, C, 25 nano, 25, and inductance, which is 25 milli. Okay, so the idea is you can do all your calculations. Okay, you can do all your calculations and simplifications using the symbolic values, symbolic terms, R, L, and C. And then later on, towards the end, plug in the value. Okay. So all to remind you, what we have done here is simply an application of KCL at this node. We did that, something very similar in the last class, except that we were writing up equations, right? The current in this guy, C dV by dt, The current in this guy was the integral of 1 over L, right? And then L di by dt. I is um, V of t dt, 0 to t, right? That's the voltage of the current in the inductor. So what we did was to set up equations for current, and then this current was summing up to the current in the capacitance, current in the resistance, plus current in the inductance. That's exactly what we are doing here, except that we are bypassing, okay? We are bypassing the integral differential equations, okay? We are simply writing the equations in the S domain form. You see, you want to pay attention to the fact that in the time domain, this was IDC. But when you convert it into frequency domain, it's going to be IDC over S. Okay, IDC over S. So once you do that, you should be, so it's a matter of simply applying Kirchhoff's current law, okay, or Kirchhoff's voltage law as necessary, okay, as necessary. But once you have these ZC, R, and ZL, you should be able to apply the very familiar circuit analysis tools that you have picked up in Engineering 17 and arrive at the solution. Node voltage method, mesh current method, so on and so forth. So if you're asked to find the value of V, you can find the value of V, plug in the value of R, C, and L, and you'd get an expression for V. If not, you're asked to find the value of IL, if that is what is asked, then you would calculate V over SL and then plug in the values for RC. Questions, please. Let's see. What questions do you have? Circuit analysis in the S domain is very, very simple. All I have done is to replace the capacitance with 1 over SC, replace the inductance with SL, provided that the initial conditions are 0. It's that much more easier. Let us see. Okay. So that's the idea of applying Laplace transform S domain or solving your circuit analysis problems in the S domain. Let's see what else. The partial fraction expansion. Sometimes you may have to do the partial fraction expansion when you want to convert. So when you do this analysis in the S domain, you get your answer in the S domain, IL. Okay, but if you want to get the IL from the S domain back to the time domain, the lowercase time domain, then what you have to do is partial fraction expansion. Okay, notice that this is a proper fraction. You can factor it out. So as a matter of fact, this one problem does quite a few number of, it does cover quite a few, at least 3 or 4 of the exam problems. Okay, so it may be a good idea for you to very carefully go through this problem. Okay, I can tell you that just by looking at this, You should be able to do problem number 6, problem number 5, maybe problem number 1 and 2. Okay, so that's about 2/3 of your exam, just this one problem. Okay, provided you not just 2/3, seems the whole damn thing. There is the initial value, and then there's a final value theorem as well. There's a final value. Okay, so it's about 80% to 100% of your exam is covered in just this one problem. I ask you to go through this carefully. Okay. Now, provided you work on this example problem all the way till the end, which includes factoring this out into its complex conjugate roots. The denominator here has complex conjugate roots. S is one root. This guy is the second root, and its complex conjugate is the third root. Okay, how do you do this? How do you find A and B values, and from there get the time domain expression using table? I think it's 12.3. Okay, table 12.3 tells you how to go from this form, the partial expression form, partial term form, to a time domain form. Okay, so this guy is your final time domain expression. That's your time domain expression. So there's a method to madness. Okay, there's a method to madness. A value is given to be 24 into 10 to the negative 3. And then, so that A is showing up here. Okay, and the B value is 20. B value is 20 milli angle 126. So pay attention to the fact that there is a 20 angle 126 in your final answer. Okay, and the 10 power minus 3 is taken care of by the milli over here. All right, so not just that, there are other terms as well that relate here. Okay, so the idea is that you have the J 24,000 that's showing up here. Okay, and then negative 32,000, okay, which is this guy, that's showing up here. Okay, so in other words, the roots of this expression, okay, the roots of this expression and the values A and B, if you know those values, you can simply plug them in and find out the value of the time domain expression. Okay, so now transfer function is simply so that's about applying this guy in the S domain, applying the circuit analysis techniques R, L, and C in the S domain. Okay, then there is the transfer function, which is simply the output. The response is simply meaning the output in the S variable over the input as a variable of S. When you do that, when you massage your equations, okay, so if you have a circuit that looks like this, a parallel combination of R, L, and C, okay, then you can calculate the impedance, which is the parallel combination of R, parallel with L, parallel with C. Okay, you get an expression for that. That's the admittance. 1 over that is the admittance. Okay, now we can find the value of 1 over RC, 1 over LC, so on and so forth. But then if you're asked to find the poles and zeros, well, that should be straightforward to do as well. Remember, let me go back. If you have, okay, if you have if you have a S-domain polynomial in the denominator, we can find out its poles. Okay, that's the idea. So simply the transfer function meaning output over input. That's the definition of transfer function. Okay, the poles for the denominator of h of s, the poles for the denominator of the h of s must lie in the left half plane. Okay, for a bounded response, stability considerations. If not, there may be unstable situation that we're talking about. Let's see. So it's just a matter of, so when you're asked to find the transfer function, you have to look for V out of S over V in of S. Okay, or whatever is the output and input variable defined to be. Okay, so in this example problem, you're asked to find the admittance. Okay, admittance is simply 1 over R plus 1 over ZC plus 1 over ZL because they're in parallel, right? So Z equivalent would be this guy. 1 over Z equivalent would be that guy. Okay, so that's the admittance. Admittance. Y is the admittance. Okay. From there, the admittance has this form. Okay, this form. So you can see that the denominator, there's only one term, S term, that corresponds to the pole is 0. Okay, there's a pole at 0. Okay, whereas there are roots of this quadratic in the numerator. The roots of the numerator are called zeros. Okay, therefore, there's a 40k plus j30k and negative 40k plus j30k. Okay, so negative 40k, negative j30k is this guy. Okay, and negative 40k, positive j30k is this guy. Okay, the roots of the numerator and the denominator can be interpreted to be zeros and poles, respectively. So transfer function in partial fraction expansion and sinusoid steady state response. This is all material that Rustato talks about. But what you want to remember again is that the output, okay, the output has a steady state response and a transient response, a frequency dependent component and a frequency independent component. Okay, so if you're asked to find the impulse, if you're asked to find the step response, okay, not an impulse response but a step response, what you can do is to take into account the initial conditions of the capacitor, and then set up a KVL around the loop. Okay, set up a KVL around the loop, and then solve for an expression for V of S, I of t. Okay. Let's see. Questions, please. What questions do you have? Let me do this. Let me go to the exam and see if you're able to check the answers. Okay. Yes, it does appear that you're able to test your answers. Okay. Other questions? What other questions do you have?
Professor?
Yes.
I'm not sure if you went over this already, but on the homework, it's a lot of multiple choice for the Laplace transform. Will it be like that for the midterm?
For the Laplace transform, right?
Yes. Since it's going to be heavy on chapter 12, and that was Laplace transform, is the midterm multiple choice, or how do we input our answer?
It's not multiple choice, it's fill in the blanks.
Okay.
It's fill in the blanks. So for example, let's see if I can pick a homework problem that is similar, okay, to the exam problem. And let's say something like this, okay. You're still able to see my screen, right?
Yes.
Okay. So I'm looking at one exam problem, well, not an exam problem, but a homework problem that is very similar to, let me make sure. Okay, just give me a second so I don't inadvertently give out the exam question. Okay, I'll pick an example. So to the short answer is it's a fill in the blank type question. Okay, but here let's take an example. Okay, f of s equals to 18s squared plus 66s plus 54 over s plus, oops, what did I do? S plus 1 into s plus 2 into s plus 3. Now the exam question reads, find the partial fraction expansion of this guy. And then there are fill in the blanks. F of s equals to dash, okay, by s plus 1 plus s plus 2. You're supposed to fill in values, plug in values for that. Now, if you did this properly, if you did this the proper partial fraction expansion method, you would find that I'm assuming that you know how to do this. You'll get with 3 by s plus 1 plus 6 by s plus 2 plus 9 by s plus 3 to be the equivalent of this guy. Therefore, you have the values for. So you get the idea, right? You simply have to fill in the blanks. It's easier. One thing I will tell you is if you have done your homeworks thoroughly, you're going to find it, find the exam easy.
That makes sense. Thank you.
Okay. So is everybody comfortable in terms of getting from here to the answer here? Everybody okay with that? So I don't have to solve this example problem, right? So you're good. Okay. All right. So no multiple choice, only fill in the blanks. Other questions, please. What other questions do you have? This is obviously a homework problem. And I solved it for you, which I'm okay with. Okay. Okay. So if you don't have questions, I welcome you to watch Professor Tetro's videos and use this to narrow down your preparation, okay, to a more focused effort. Okay, start your preparation here, and then after you're done with these topics, you may want to expand on other topics as well.